can the representative from Expo start recording? Okay, perfect. Thank you.
I just started, but I can wait 2 more minutes if you prefer.
It's fine. You can probably just cut
Okay.
off for 2 minutes if it's that
Yep.
perfect.
Of course. Thank you for being here today, Ethan. We appreciate you.
Well, thank you for setting up Expo and making sure it actually happened this year. I'm really glad that we were able to
Of course, we're really happy to have you.
Let me just make sure I have everything set up. Can you guys see the phone camera as well? I'm trying to give like 2 camera angles so everyone can kind of see the project with a little bit more detail. Yes, no? No. Interesting. What about now? I can only see one camera. Interesting. Well, I will do my best to make things work with my tablet camera. Okay. Well, it's 5:03, so welcome everybody to the 2021 Engineering Expo. This is the Biomedical Engineering Society. I'm Ethan Daniel. I'm our R&D chair. I'd like to welcome you today. I've got 2 projects to show you guys. So the first project we've got is right here. You guys can see it, hopefully. This is the arm wrestling EMG machine. So this is a device that allows 2 participants to sort of remotely control an arm wrestling machine, which we 3D printed, by taking signals from their biceps using electrodes and wires, so that when they flex, it's able to see that signal and see who's flexing harder and who's flexing like stronger, and the device picks a direction based on who's winning that battle, and then moves in that direction, so they can sort of play that game without actually physically touching each other. Very COVID friendly, so very timely project, since with these wires someone can be 6 feet apart and still arm wrestle. So I'll go ahead and show you guys kind of what this project is all about, and sort of break it down for you guys. So like I said, we 3D printed this actual device itself, the whole structure. So it's all built from scratch by the Biomedical Engineering Society. And as you guys can see, it's like one big structure. So I'm actually going to move this camera here. If you guys can see, here's the actual servo motor that controls the inside of this device and actually moves the arm left and right. This is actually one solid piece. The hands, we don't have them like clasping because that would be more difficult to design. And we've just got 2 rotating elbow joints. So it's actually symmetrical. So say this side broke, we could also take this servo motor and just plug it into this side, just in case. So that's the sort of like cool engineering design prospect. Someone's waiting in the lobby. So if you guys can see these wires here, they actually go down to this thing right here. Can you guys see that?
I think we can see only one camera. It's yours.
Which one can you guys see?
Your face from the side.
From the side? Okay. What about now?
Yes. Now we can see.
You can see it now.
Okay, awesome. Thank you. So this device right here is actually two pieces. This bottom part right here, this board is called an Arduino Microcontroller. So the cool part about an Arduino Microcontroller is that you can program it to do various things. It can record data. It can tell devices what to do by outputting electrical signals. There's all types of different things that can be done with it, and it's used in a ton of different projects. And this part actually right up here is a circuit board that BMES R&D team soldered together by hand. And each of these little kind of small black bug looking things are amplifiers. So what's important to recognize is that since we're working with a biosignal here, we're working with a really, really low signal because human beings aren't really like very electric per se. The electrical signals that control your body are in like the thousandth of a volt scale. So it takes a lot to pick them up. So you need something like an amplifier to sort of multiply that signal by some gain so that you can actually see it. And I'll actually share it my screen here in a second, and you can actually see the signal for each input, and there are of course two. As you guys can see, here are the wires that lead to the electrodes that get placed on the participant's bicep, and there are three here. On this side, two of them are red and one of them is black. Can anyone guess why one of them is an odd color?
It's a negative signal.
Close.
Or the 0 or positive.
See someone typing in chat as well. From an electrical engineering perspective, you'd be right, but from a biomedical engineering perspective and a signal collection perspective, it's a more specific answer. It is the ground. So that these two signals, these two red wires actually measure the signal on the bicep itself. So one goes right here, kind of towards the elbow, and one goes kind of here towards the belly of the bicep, which is the top point. And this black cord actually goes all the way down your wrist and acts as ground. So that's like the reference point for the other two signals, because right there, it's just simply a difference. If there wasn't that reference point, it'd be a lot harder to tell what that difference is, because you wouldn't be able to eliminate all the other sounds, the electrical signals coming from other parts of your body. Since everything in your body is controlled by electrical signals and chemical signals, it's really hard to isolate them and record them. So you need something like a ground so you can subtract all the rest of the signals coming out of your body, like your heartbeat, your brain waves, anything like that. And that sort of cleans the signal up. So that's a really, really important component of the project. So now I'll actually demonstrate it, which means I get to put on a bunch of electrodes. So let me take off this metal bracelet. So another important part of biosignal collection is the use of electrodes. So if you ever are watching like a TV show or a movie and you see someone with a bunch of like wires stuck to them and stuff, they're usually connected to these things, which are electrodes. And they're nothing fancy. They're just a conductive material that is like adhesive, so it sticks to your skin and helps kind of ignore that skin resistance. And makes collecting signals a lot easier. Your skin is actually pretty resistive. as in like it blocks electrical signals from coming in and coming out pretty well. It's not it's like insulatory. It's not very conductive, which is why when you get electrocuted, like it's like a burn because it doesn't conduct very well, so it heats up. It's a fun fact. But so like I said, the black one goes on the wrist, and the two red ones go on the bicep. And like I said, this uses an Arduino microcontroller. So what's really good about Arduinos is that they're widely programmable. There's a whole bunch of different stuff you can do with them. And for this project, this one Arduino is like inputting a signal, measuring it, telling the computer what the signal is, and also at the same time using its internal programming to tell this device what to do. So let me open recent. And you guys saw like that blue cable that connects to the Arduino. That's like the main. Oh, hello. So part of the programming sequence is as soon as it turns on, it starts at the neutral position. You can see that it's going to slowly turn towards me because I'm only connected on one end, right? So it's not recording a signal on the other end. So obviously, if I just flex, it's going to eventually win in one direction. And it wasn't turning towards me, actually. It was turning the other way. I don't know why I thought that. And like you can see, it goes back to neutral position. All right. I'm about to share my screen. Let me know if you guys can see this. Can you guys see that? It's just a jumbled.
Yes, we can see it.
Awesome. So it's just a jumbled mess of lines at this point. It doesn't mean anything. So let me break it down for you. If you guys can see, each line has a different color. The really only two ones that we care about right now are the yellow line and the green line, if you can see the difference. The yellow line and the green line are the strength of the signal coming from each participant. So on the red and black side, it's represented by the yellow line. And on the green and yellow side, it's represented by the green line. If you guys can see, there's also red and blue lines, which represent kind of like the frequency phase of the electrical signal itself. It's just part of the processing. And you guys will probably see later, they can get like really choppy and they actually look more like an EMG signal. Whereas the line at the top is just like the progressive amplitude that's being added up over time to kind of give an idea of how hard that person is flexing. And the purple line is the combined ground from both. So when one is connected and one isn't, it just shoots towards negative. But when both of them are connected, it'll stay pretty even on the middle. So I'll demonstrate that one more time because you guys probably didn't see too much of it. Alrighty. So as you guys can see, the yellow line is like bumping a little bit as I move my arm, but if I flex, it shoots straight up and that electrical phase signal starts getting really, really choppy because that's what the actual electrical signal looks like. Does anybody have any questions up to this point?
Like just out of the curiosity, like on the y-axis is the signal, it's in voltage. It's
Yeah.
signal strength. On the y-axis, like it's a 5, 10, -5, -10.
Yeah, that's signal strength. I'm not sure if it's exactly in volts because I don't remember what the gain ratio was on the amplifier we built. But it's mainly just there as like a relative representation. And I'll show you guys later. I'm actually gonna hook up both my arms to see like if there's gonna be a different signal because you know it's the same body. Why you know is it gonna be able to isolate two different arms? We'll see. But it's
Thank
mainly just there for relative. But yeah, the y-axis is voltage strength or signal strength in voltage. Any more questions? Alrighty. Well, I'll go ahead and hook up both arms since we can't have two participants this year because of COVID. I thought it would be interesting to see like how accurate this device would be in measuring the signal between two different parts on the same body. And so, what do you guys think will happen? Because I've obviously already tested this already, but I had a couple ideas beforehand because I thought it might be kind of weird. What do you guys think will happen? Do you guys think it'll be accurate? Do you guys think there'll be a lot of noise? You guys think it'll be the same signal? No guesses? That's fine. Lots of noise. Okay, that's a good guess. That is also what I thought before I did this. We will see if you are correct. Any other interesting guesses before we go? I'll switch to the other camera so you guys can actually see, hopefully. All right, can you guys see?
Yes, we can see you.
Awesome, thank you. So, I can keep this from disconnecting and sticking to everything. Oh. So, we'll see what happens now if I can actually control it with both arms, and then we'll look at the signal. So at the beginning, you have to start with your arms relaxed, otherwise it's going to take a neutral position and set as the baseline. And it doesn't look like it's working now. Let me reset it. Arduinos come with a really handy reset button on it that automatically restarts the code whenever you hit it. So let's say like something's not working, like for instance right now, you can just automatically reset it, or you can unplug it and plug it back in like a true engineer. Oh, hello. There we go. All right. So right side's winning. Let's see if I can bring it back. Nah. This is actually like really difficult because you have to flex at the same strength the entire time. Otherwise, it'll stop. And now it's like back to even, right? So it kind of emulates real arm wrestling where it gets harder and harder as you keep doing it. So if I switch back to flexing my right arm, it starts to push the other way. And then if I switch back to my left arm, there's not enough time for the voltage to build up because it kind of trails off. I'll go ahead and share the signal screen so you guys can see exactly what it looks like. Alrighty. recording. Interesting. Here we go. Sorry, having some technical difficulties as usual. All right, can you guys see that? So, okay. Let me see if I can get that to run again without it being impossible to share. Alrighty. So it's running now. You guys can see the yellow and the green are kind of right next to each other because I'm not flexing either of my arm. But if I start flexing my right arm, the yellow shoots up. There's a lot of noise there. If I start flexing my left arm, it'll start to come back. And the blue has a lot of noise. I start flexing my right arm, the opposite happens, but at that point, it's kind of too late. So it's still pretty accurate down to like almost the second. As soon as I flex, it starts to change directions and starts to peak up and peak down. But there is a lot of noise because you guys can see the actual signal itself becomes really, really noisy. And if I flexed both at the same time, they both just kind of start jumping towards each other. And this is actually only possible because between these two signals, we've calibrated this device actually, because obviously all electronic components have some sort of error in them, right? So not every capacitor and not every amplifier is built the same. So each of these has actually a different individual gain. Like each arm and each participant has a different individual gain for this this device. So in the middle of the circuit where they both meet, and they're, or between the circuit where they're, before they both meet and actually like the signals are sent to the board, we have a transistor, which not a transistor, a potentiometer, an adjustable resistor, basically. So we can kind of favor one signal or the other. So this can also be used to like rig the game if you're trying to play a prank on somebody. But those sorts of electrical components are really important when it comes to building circuits because, you know, without each of those components, we wouldn't be able to build the complex like devices that you see in like medicine and whatnot. And kind of how this sort of relates to like, you know, we're the Biomedical Engineering Society, so like how this sort of relates to medicine is in like that sort of signal collection you see in like TV shows and movies. Like people, when they're in the hospital, they're hooked up to a bunch of devices. They're hooked up to like electrodes, a heart monitor, they got an SpO2 monitor, a whole bunch of stuff that tells the nurses and doctors a bunch of important information about their wellness, their state, their vitals, everything like that. So this technology is really important in the modern world of medicine because it tells everybody, you know, how the patient is doing. And also a way that this could be applied is in the future of prosthetics. So controllable prosthetics are already being developed today for people who have lost, you know, let's say a quarter portion of their arm. There are still a lot of muscles that are still intact. So if those muscles can be retrained to be flexed in certain ways, then just like in this device, that flexing can be measured with a more accurate setup. That's obviously more well designed and industrialized, and it can be used to be like to move an actual prosthetic in certain ways. USF is actually works with a guy who has a prosthetic arm that is from just above the elbow down, and he's trained his tricep and bicep muscles, what remain of them, to help move that arm's elbow and wrist. So the future of this sort of technology is really, really interesting. So forgive me for rambling on about it for too much. So that's about all for our first project. This is the EMG arm wrestling machine. Does anybody have any questions?
Hey, Daniel, you just talk about the prosthetic arm, and is there any relation for with the neurons in the muscles, or they are simply taking the signal from the muscles like electric signal? Is there any relation to the neurons or something?
So,
Actually, I'm not a biomedical student, but I'm just an electrical student. But I'm out of my curiosity. I just want to know how the accurate prosthetic real life implementation, like they work with the neurons or some kind of synchronization with the neurons signals.
so as far as I know, you would need like a sort of like invasive electrode to be able to measure like the neural signal itself. But generally, what an EMG does is when like a muscle flexes, like a lot of calcium ions are released. So there's an electrical gradient that forms as soon as that muscle is like triggered by a neuron. So essentially, like there is like obviously some delay, but it's getting the neural response. I don't think they're able to like. Well, they probably are, but I don't think they're able to from the surface of the skin. I don't think they're able to like isolate individual patches of nerves. I think it's easier to isolate individual muscles and train a patient in some situations. But I think that's a really interesting way to approach that is to actually like look at the neural signal itself, like the electrical signal. But normally it's the electrical gradient caused by a rush of a chemical signal.
So basically, that signal generates from the muscle's power.
Yeah, from them just like emitting a bunch of calcium ions at once and seizing.
Interesting. Thank you for the information.
Absolutely. I'm really passionate about this stuff. So if anybody has any more questions, I'd be happy to answer them. But I'll go ahead and show you guys our second project. This one kind of operates very similarly, but relies on a little bit less accurate technology. So we're going to try our absolute best to get it to work. I also don't have a ton of space to make it work and demonstrate it. So we're going to try our best with that one. But give me just a second and I'll move over there and set it up. Alrighty. Second. Kind of have to have a platform so that you guys can see everything. But here is the second project that we have produced, kind of along the same lines as the other one, but in a very different direction. This is called the EOG controlled wheelchair. So engineers are obviously the most creative people on the planet. So we like to kind of name everything the same and just change one thing at a time. So whereas that's like EMG, which is an electromusculogram, this is an EOG thing, which is an electrooculogram, which has to do with the eyes. There's also like an electroencephalogram, which is like signals from the brain. They're all the exact same thing. They're just collecting electrical signals from somewhere in the body. The middle part just changes based on where it is. So, like I said, real creative. But this one is a 3D printed model wheelchair that we have built. And it's actually Bluetooth connected to this receiver box over here, which is also 3D printed, that contains sort of like a black box of different circuitry, which I will show you guys a little bit more about as I walk you through it. But there are Bluetooth connected, and whereas the previous project used stick-on electrodes, This one actually uses these little spike electrodes. I don't know if you guys, how much you guys can see these, but these actually just rest on the surface of your skin. And this is actually a custom printed plastic set of goggles that we had made out of this more flexible plastic material, whereas this is a lot harder 3D printing filament. And this can measure with these different electrodes. It can measure which way someone is looking. More accurately, it can measure which way someone flicks their eyes. So, for example, like a quick eye flick is like when you're looking straight down the middle, and then you look to the right and then look back down the middle, right? So this kind of operates by measuring those signals, and within this black box, or red box, I should say, there's another Arduino, just like in the last project, that is programmed to filter these signals out. Because if you guys thought there was a lot of noise with the arm signals, there's way more noise with the much smaller signals that are coming from your eye. And it then tells through the Bluetooth transmitter to the receiver over here, it tells this Arduino, which there's another one actually sitting in the lap of this chair, to power these DC motors that are chilling in the back here, connected to the wheels. And the wheels are actually wrapped in cheesecloth to make them like frictionable, because this 3D printing filament is like a hard, slick material and wouldn't really roll well on anything. So we made like that slight modification. We had rubber bands on there, but from being under the constant tension, because obviously rubber, like tires would be good, but from being under the constant tension of being around the wheels, they eventually snapped. So that was a design change we had to make. So to kind of get ahead of a question that someone asked last time, the way this actually measures a signal, the signal it's actually measuring, has to do with the way the eyeball is shaped. So I don't have a good anatomical model, but everyone kind of knows that the eye at the front is like the iris, the pupil, and everything, and the back is the retina. So on the back, there's actually a lot of negative charges, and on the front, it's more positively charged. So there's an automatic dipole wherever you're looking. So when you look to the right, that dipole, and a dipole is like a spatial difference between two electrical signals, right? It's a spatial gradient, or an electrical gradient in space. So that dipole, when you look to the right, turns to the right. And that dipole, when you look to the left, turns to the left. That dipole, when you look up, goes up and then down. And then when you blink, your eyes typically go down a little bit. And a bunch of muscles in your face contract, and it destroys the signal. So we actually utilize that as part of the project itself. So we have it turn left when you look left, turn right when you look right, go forward when you look up, and when you crash it by blinking and overloading the signal, it stops. So it's a kind of intuitive device that is kind of really hard to operate because you can't really look at it and control it at the same time very well. So this wouldn't necessarily be used in a hospital setting, obviously, but you guys can see sort of how the concepts involved here could help someone who's maybe disabled or has some sort of mobility impairment operate a device without using their actual physical movement, or with using very small movements that are picked up by an amplifying device and that tell whatever they're trying to operate what they need to do. So that's sort of the potential future of medical technology in making people's quality of life a lot better. So we're going to demonstrate this and see if it actually works. I don't mean to say that as if I don't have faith in it, but I mean to say that as in Bluetooth with Arduinos is unfortunately not very reliable, and it's something that's being developed over time. So what's really important to do with these is to use some sort of gel. So if you guys saw those sticky electrodes had like that sticky substance on there, and that is like made out of this stuff, which is like electrode gel. And it basically just increases the conductivity of your skin. So what you do is you basically put a little like dab wherever one of these is going to be. And I wish I could get a better camera angle for you guys. Let's see. This is probably a lot better. Let me know how well you guys can see. Oh, yeah, that's a lot better. Okay. All right. So I'll actually talk about this a little bit first before we try to demonstrate it, because I'm sure you guys want to know all about what's in here. So there are actually three main components of what's in here. This is just like the other one. It's a hand soldered relay of amplifiers. You guys can see there's a lot more like complicated circuitry going on there. The reason for that is, like I said, the signals coming from your eyes are a lot more complicated, harder to read, and there's a lot more noise. Coming out of this side, without the actual backing, at the bottom you can see the Arduino that's being used. And on top, this extra circuit board here, or this extra circuit here, is the transmitter part for the Bluetooth. And this button is the emergency stop button for the wheelchair. And this small LED kind of tells you whether or not you're connected, A, and B tells you which direction you're looking based on red, green, and blue. So now we'll actually try it. So unlike the last project, which I actually had plugged into my laptop, this one showcases kind of the full power of Arduinos as programmable devices, since they don't really require a computer to run. They just require a power source once they've been programmed. And once they've been programmed, they'll constantly run that program till pretty much the end of time. So you guys can see it's connected, which is good. Or it's reading a signal from the goggles, I should say, not connected. That's not the Bluetooth connected button or light. That's actually on the Bluetooth module itself. Get good spacing for this. So you guys can see these are like exposed circuit boards, right? So in most industry products, these aren't allowed because the potential for shorting and wires coming undone is pretty high, which is what I'm checking for right now. In most industry settings, what you'll see are printed circuit boards, which are those little green circuit boards that you see in pretty much every electrical device these days that's programmed, and they or that just has a circuit in it, and it automatically prints whatever circuit you need based on a schematic. So they're really, really convenient. So I don't know if you guys can see properly here. This little red light here on the Bluetooth module is now flashing, letting us know that our Bluetooth is connected. So we're going to check all the connections here and make sure they're solid. And then We're going to cycle power since this wasn't connected when it started reading signals. Okay. So I'm just testing and see if it's actually talking to the other device right now. Go ahead and reset that. Oh, there we go. Is there not enough power? What's wrong? So let me try this one more time. So one issue here that I think might be happening is that this all takes a pretty decent amount of power, this whole setup. And this one 9-volt battery may have been already kind of drained. So what I'm trying to do right now is make sure that everything is connected. And it looks like it is. It should be getting some sort of signal. All right, so looks like we're running into some technical difficulties. I'm not exactly quite sure what's wrong because both of the Bluetooth modules are connected. Checking to make sure there's not short somewhere. That's plugged in. That's plugged in. Interesting. So let's see. All right, I'm gonna try cycling the power one more time. They're connected. So I'm not quite sure what's wrong. However, essentially you guys should be able to get the concepts. I'm going to try to troubleshoot this for another few minutes, but in the meantime, do you guys have any questions?
I guess both the cards are communicating with each other, but maybe battery has some load issue. draining the battery.
Yeah, I'm gonna try it with a different battery. I'm also gonna check all the connections in here to make sure that none of them came undone. Because if on this side anything is not working, that will spell disaster. Okay. So you guys can actually get a better look at all three of the components here. Here's the LED. All the components are set there. Control, ground. This is powered. Alrighty. Just make sure all these are not touching. That's grounded. So the most important thing is to always make sure everything is grounded and connected. And now, let's see if we can get things to work. Okay. They're connected. Oh, there's an active short right there. That's probably a problem. All right, so it's reading a signal. So right now it's reading red, so I'm just looking straight forward. Now it's green for up. Trying to get blue for left. Right. It's having trouble picking up. Oh, there we go. So I'm going to see if on the board over here, I'm going to see if I can power the DC motor separately, actually. And see if that works for us.
Give me 1 second, guys. I'm trying to rewire everything to make sure that there aren't any misconnections. Alrighty. Okay. So I'm gonna get a new battery and try it with that. That doesn't work. Alrighty. Alrighty, so to try to overcome the power needs here, I'm going to try to power the what's it called? I'm going to try to power the one moment. I'm going to try to power the motors themselves with a separate 9-volt battery to see if that works. And if not, then unfortunately we'll just call it a day. But I thank all of you for sticking around up to this point. I'm just gonna go ahead and try this now. Powered, connected. All right. So let's try this again. If we can get this to work, we'll call that a huge success. If not, we'll call it another day of engineering. So the first part of the program actually takes a baseline measurement of where you're looking. So you're supposed to let your eyes relax and look at the middle. So it's easier to come to either side and take a measurement. Right now, I'm not really doing that. I'm paranoid that there's another short. All right. Right now, for some reason, this is not being powered. Oh, so this became disconnected over here as well. It's unfortunate. Okay, so they've connected. Alrighty. So now this one seems to be having trouble picking up that signal. So it looks like it might just be another day of engineering. All right. Unfortunately, it looks like this isn't going to work today. So we'll give it one more college try with the old battery setup. And after that, we'll just call it. Those are all connected. This one isn't. Alrighty. All right. As you guys can see, it's quite difficult to wire things when your hands are way bigger than the wires. A lot better. Okay, and it came undone again. All right. Now we'll see if that works. Still powered. Reset button. Reset button. Oh yeah, this battery is 100% dead. Interesting. All right. This one should be picking up a signal. They're connected. See, now we're not even seeing the LED pop up, and that is concerning. All right, guys. Looks like this one is just not going to work today. We tested it out earlier this week, and it did work. I'm not exactly sure what the problem is right now, but I thank all of you for sticking around for the last few minutes while I made myself look like a fool. But to talk a little bit about that project that kind of looks into like the solutions for people who have some sort of movement impairment. And it takes into account a lot of different engineering concepts. So we've got a 3D printed wheelchair. Everything we've done here, we've programmed and built from scratch. We've got the concept of a printed circuit board within biomedical electronics. And you've got Bluetooth communication, which is a new, well, not a new, but a growing field that is relatively young. And is going to be used in pretty much everything in the future because it's so efficient in some ways, and in other ways it's sometimes inefficient. Oh, now it's getting a signal for some reason. Don't tell me it's going to start working. The light just turned on.
Daniel, I have a question, like how the wheelchair is moving on the left or right direction? Like, is the front wheel is controlled by any motor or something? Or
So, okay, just the two back wheels are controlled by the motors, right? So the right and left turn commands are like this motor turns backwards and this motor turns forwards to turn right.
Oh, that way.
And vice versa.
Take turn right or left.
Yeah. So like if you're moving and you tell it to turn right or left, it stops and it turns right or left for however long basically you looked, and then you can start moving again. But the point of that is to essentially like keep it stationary, because if you try to turn it while you were moving forward, while you're looking at it, and you're looking in different directions, you're going to lose control pretty quickly, which is something we found out when we were testing it. But I'm sorry that it didn't work today for everyone. I'm glad you guys got to see it. Does anybody else have any questions? If not, I want to go ahead and thank everybody for their time. It's been a great thing to see Expo happen again this year, even despite all the issues with COVID and whatnot. And I'm glad that everyone showed up today to see the Biomedical Engineering Society's projects for the year. We'll see you guys again next year for Expo, hopefully in person, but even if it's not, I'm sure we'll find a way to work around it, because that's what engineers do. If you guys are interested in joining the BMES R&D team, those of you who are USF students, feel free to check out our BullSync for links to our Microsoft Teams. And if you guys have any questions or anything, let me know. If not, we'll go ahead and wrap things up for today. Thank you all so much for showing up, and I hope everyone has a good rest of the week.
Thank you so much, Ethan. This was great.
Thank you guys so much for hosting this.